All right, well, welcome to Chapter 5 lecture on arrays, and hopefully you've had a chance to read the chapter. If not, then you should probably stop this video and go read it and then come back to the video. We've talked about variables and how you declare them and that they are a segment of memory whose name that you've given the variable points to that section of memory, that location. And using the name, you can, either put variable values in there or delete them or things like that, concatenate if it's a string. Arrays are very much like variables, and they are variables, only they are contiguous memory locations. That means back to back, and they have one name, but they can only store one data type. But by using indices, 0, 1, 2, 3, and 4, you can access each block of memory that is contiguous back to back, going from 0 to one less than the number of elements in that array. So if I have 5 elements in there and I start at index 0, it's one less. So if I have 5, the highest index, or the last index, is going to be one less than 5, which is 4. Okay, and we'll get into that a little bit more. But okay, and I've already basically said this, but it allows you to store multiple values in with one variable name. Essentially, is what it does, and that has its uses. Helps you organize your data better. And as you can see in class 7, we use 2 parallel arrays. So basically, you need to tell, when you declare it, you tell the compiler the name and how many elements you need in it. And you can initialize them and it'll do it. There are a lot of, depending on the language, how it's done. Visual Logic uses make array. Again, I've done that particular in-class lab for you. There's a video out there for it. So the subscript's also called an index, and it indicates the position in a particular item in the array. So you always start with 0, and the size of the array is the number of elements in it. The highest subscript allowed in an array is 1 less than the array size. And that's called off by 1 error. Most people will do. They'll go outside the bounds of the array because they were looking at the last element instead of the last highest index. There's a difference. Here we have an array called sumVals, and it's in memory somewhere. Looks like integers, and the first index is index 0. It contains the value 25. The next index is index 1. It contains the value of 36, and the final or highest index is 2. It contains the value of 47. This is the blocks of memory that are contiguous. They have to be the same data type because they have to be the same size. And you've got one name that you can access all these different boxes. Now notice how many elements are in here. There are 1, 2, 3, or items, you could say. 1, 2, 3. 3 blocks of memory, 3 items. But since we start at 0 and 0 is a number, then 0, 1, and 2, the highest index, which is 2, is 1 less than the total number of items. We have 3 items, so the highest index is 2. If we had 10,000 items, the highest index would be 9,999. All right, it's just that simple. Okay, here is, we're declaring this particular array called sumVals of type number, and we're saying there are 3 elements in here, okay? 0, 1, and 2. That's just telling how many elements there are. Each language, some languages are different. Visual Basic.net requires that you give it the highest index, so we would be given this 2. But C++ wants the total number of elements, so it just depends on the language, but for all intents and purposes, that's what we're doing here. Now, Visual Logic requires the highest index. You'll see that in class lab 7. So don't get confused by that. That's just a syntactical difference. So there are 3 elements in this array. 0, 1, and 2 are the indices, 1, 2, and 3, the 3 elements. You can also declare it and initialize it in one string. You could do that. Okay. All right. You could stop and watch the video on your own. I'm not going to go through that in my videos, but you can use constants, which I did in class lab 7. I used a min and a max constant. Min was 0, max was 4. You'll see that when you go through it. Accumulating, you use a loop to traverse an array. If you want to accumulate all the values in an array, if that's something you need to do, you just start at index 0. Your loop counter will parallel the indices of the array. So you go from 0, in this case, to 2, and you'd loop through index 0 and add it to a counter, and then you'd loop and grab the value at index 1 and grab the value at index 2, and then it would exit. And you would have the accumulated value, or the sum of all those values. Again, you can watch this video. And when you're doing a search, you search or you traverse the array with a loop. Start index 0, go all the way till you find a match if you're looking for a given value. And you'll have a flag of some sort that would either exit the loop or tell you at what index you found it. Now, there's optimization issues. If you're looping through an array that's coming from a database and it may have 10,000 records, and you find a match for the item you're looking for at index 3, there's no need to run all the way to the end of that data set. You just exit the loop once you found a match. Okay, so that's processing optimization. And here's she goes through, the author does a real good job on the videos of explaining some of this stuff here. So you got valid item, found it, and there's your 106, 108, 307. I guess those are item codes of some sort. And so as long as your sub is less than size is a constant, I'm sure, yeah, 6, then you keep looping. So, and you're incrementing your small case sub. Now in this case, there is no optimization. It goes all the way to the end, okay? But it's a flag that tells it that if it found it at the end. Now that's not optimized for, speed, but it's okay. They'll get to that. And that's your pseudocode for the same thing. Those are parallel arrays, and if you look at what I've done in Class Lab 7, that perfectly describes the relationship. One of the arrays is the part number, and the other is the price. And since they are parallel, if you find an item at index 2 that's the right part number, then you also look at the price array with that same index because they're parallel, and that will give you the price for that part number. And here's basically the same thing. There's a valid item. That's probably like an item number or part number. And there's the price associated with it. They are parallel, as you can see here. So if I ask you to give me the price for item number 307, what would you do? Well, you could just visually look down here, just in this chart, you see that it's 4.5, $4.50. But if you were looping through this array, starting at index 0, and they said, you got a value from the user, find part number 307. Well, it would first look at this, and if it didn't find it, it would increment it, go to the next one. Look at that. If it didn't find it, increment it, go to the next. Well, there it is right there, 307. So you already know, based on your loop control variable, which is your counter, starts at 0, 1, and 2, that you found that item at index 2, and you would look in the price array at index 2 to get the price for 307. See that? Those are parallel. That's how that works. Okay, so that basically is showing you how it found it. Okay, so what it does is it stores the price once it finds it, and then it already has it ready to output here. There are other ways to do this, but they still haven't addressed the optimization issue yet. They're still looping through the whole thing, even though they found it at index 2, they're still going all the way through. Now these could be 10,000, 100,000 records, which the bigger that set is, the more ridiculous it is to keep looking if you've already found it. And there's your flow chart for that. Leaving a loop as soon as a match is found improves the program's efficiency. That's definitely the way to look at it. Larger the array, the more beneficial it becomes to exit the searching loop as soon as you found what you're looking for. Now, typically what would happen is you would connect to a database in a real program or the internet or wherever you're getting your data from, and get a data set based on some query, a database query. And that would load into an object like an array. So you may have 50,000 elements in that thing, and you're just looking at one aspect of that. And if you find it, you need to get out of that loop. You don't need to traverse the entire thing. Okay, so now they've got an and up here. As long as sub is less than size and the found it flag equals no, then you keep going. Once that found it flag is set to yes, that and is going to be false, even though sub is less than size, because both of these have to be true for this thing to be true. So that's one way to get out of it. There are other ways, okay, but that's one way to get out of it right there. All right, and you can look at her, Joyce Farrell's little videos are kind of cute, so that'll help you some. Remaining within the array bounds. Array elements have a definite size and memory. They have a certain amount of memory allocated. If you try to go to an element that doesn't exist, let's say there are 5 items in this array, and that's from 0 to 4 as far as the indices go, and you try to hit index 5 or subscript 5, it's going to throw an out of bounds error. That's a very common thing, and if you see that, that's probably what's happening to you. The number of bytes in an array is always the multiple of the number of elements in the array. In other words, if I was storing an integer, a bunch of integers in an array, and it took 4 bytes of memory for each one, in order to find out the total number of bytes, you'd multiply 4 times the number of elements. That's also how it finds how you gain access to each element using a subscript, because what it does, it takes that subscript number that you've given it, and it looks at the size of the integer, which is 4 bytes in this example. So it says, okay, find the second element. Well, it starts at the beginning of memory where that thing starts. Let's just say it starts at 0. And it says, okay, each one of these are 4 bytes long. I need to get at element 2. So to get the beginning of that address of memory, I'll take that 2 index and multiply it by 4, and that's 8 bytes. So it starts at 0 and goes 8 bytes over. That's at index 2. Relative offset addressing is what that's called. I don't know that major day. You don't really need to understand it that much, but it doesn't help to. I mean, it does help to know what's going on under the hood. Here we go. Here's a little example here of the off by 1 error. It says it's got an array of type string, and it has 12 elements in it from 0 to 11, January, February, all the months, all the way up to December. And you get the month from the user, I guess. Well, if they give you month 1, as far as the array goes, that's really index 0, not index 1. So what we're doing here is they're subtracting 1 from the month, and that will put you at the correct location because that's at index 0, not index 1. February is. So if you just took month and stuck it in here, it would give you February. When they typed in, they wanted the first month, which is January. So that's that off by 1 thing I was talking about. That's what they're doing there. And we talked about out of bounds, subscript arrays. And you can do data checking for that. We did a post-test while loop, make sure that they give us what we need. That's just data validation. You can use a while loop to traverse an array. For loops, I think, are a little easier to use because once you set them up, you don't have to increment anything. But there again, it just depends on what you're doing. There's an example of that. For start value 0 to size minus 1. Size is the number of elements in this case, 1, 2, 3, 4, 5. All right, so again, it depends on the language, but in this case, it's kind of like C++. So they set it to the number of elements, not the highest index, 1, 2, 3, 4, 5. So they're going from 0 to size minus 1, which is 4. That's their indices. This is 0, 1, 2, 3, 4, 5. That's 5 elements, but it's 0 to 4. 1 less than 5 is 4. That's your highest index, and you're stepping in by 1. So those are always integer values for your indices. So you're outputting everything in that array because dep parallels each one of these indices. Now notice that. You can use the loop control variable as your index because you don't know what, you're just looping through. You don't care how many elements there are. So it starts out at 0. All right, there's dep. That's your loop control variable. It outputs a counting. It steps it by 1. Comes back up here and looks, and up. Now dep is 2. Personnel, then 3. Technical, then 4. Customer service, then 5. Marketing, then 6. Well, we've already exceeded size minus 1, so it blows out. If we didn't do that, if we just put size in there, once you hit 6, it'd come back in here, and you would get an out of bounds error because there is no index 6. That's unreadable memory. And that's basically it.